So our next speaker is Philippe, who will be speaking on reversing an M32C firmware lesson learned from playing with an uncommon architecture. Exciting talks for anyone who's ever been fascinated and gone down a rabbit hole on an uncommon embedded architecture. This is going to be very exciting. Philippe, the floor is yours.
Thank you. Can you guys hear me? Thank you. So hi everyone. So today, I'm going to talk about the lesson I learned while reversing M32C firmware. So who am I? I'm Philippe Lolouette. I'm a senior security researcher at Trellix. I've been working with my team, Advanced Light Research, for 3.5 years. Usually I work on vuln research, on like consumer IoT, hardware, enterprise software, and so on. So you can find me on Twitter if you want. So the idea of this talk is I spent roughly like a year looking at an infusion pump. It had multiple components. One was a real-time firmware running on M32C controller. There's like a bigger picture, and you can see the blog that details all the work. I did that with my colleague Doug Mackey. But really, the point of this talk is not to go in the details of the embedded firmware itself, but rather what lesson I learned while approaching an architecture that I wasn't familiar with. And hopefully, like these lessons learned can be reused to different architecture. So how did it start? On the left side, you can see the circuit board of the pump. And on the right side, the same circuit board like slowly getting cooked on the rework station to remove the flash chip. And so that's the flash chip was removed, and it did still work, so that was good. And my colleague approached me and was like, is there code on that? So if you pay attention, you may see like a null pointer string. So you can guess that, yes, there should be code on that. But basically, yeah, by eyeballing it, yes, there is code. If you do entropy analysis, it looks at it as well. You know, like it's not crank up to 1, so it's not encrypted or compressed. But if you ask binwork, it's going to say, oh, maybe that's MIPS, ARM, or even Arcadian. I have no idea what that one is. But if you try to import that in IDA and decode stuff, it's not MIPS, it's not ARM, and I don't know, Arcadian. But what you can do is just like look at the chip, and it says M32C on it. Back then, I didn't even know it was an architecture, and Googling it didn't really help. So I keep looking for stuff, and eventually I found FDA pre-market filing, which is like a document because it's a medical device, and in it says, oh, it's a 2 Renesas chips, even tells you the programming language, the operating system, so really handy. And so yes, it was a Renesas M32C. So what you can do next is like Google all the stuff, recover like data sheets, software manual that it tells you like how the assembly works, and even the hardware manual that tells you the peripherals, the timing, and so on. And that's really nice because usually like all the chips you look at, like the weird ones, they're like under NDA, so you cannot access any documents. So on that time, that was really fun. I'm going to show a bit of assembly eventually, so just to give you a TLDR of the architecture. Register are 16 bits, they can be put 2 by 2 to make 32 bits words. You have also address registers A0 and I1 that takes 24 bits addresses. In B is the location of the interrupt table. Now that will be useful later. And technically it's a CISC instruction set, but really you just have like add, move, multiply, all the usual. And stuff go left to right, so we're going to like move 42 into R0. And yeah, there is like more complicated instruction, but you can just, you know, read the software manual. So now like the usual question is like, how do I import that in IDA? Turns out IDA starts supporting that architecture like 3 months before I started the project. So I was lucky on that one. It supports /80. The one I had was /83. I was like, it's probably good enough. Really, what's different is just going to have different like peripherals and stuff. So always the question is like, what's the load address? Because it's a flash dump, there is no like a elf loader or something. The common way is you're going to look for like absolute addresses, addresses to strings or pointers of function pointers and so on. But this time we have a data sheet, so we can leverage that. That's really complicated. There's tons of modes. I had no clue which one we were in, but there's a bunch of addresses that say like where the memory range starts. So I was like, we can try those and see what happens. An extra piece of information is at the bottom of the memory layout, so FF, FE, 00, you're going to have a bunch of function pointers. So if we load something and it has function pointers at that location, we can know that we did it right. So I tried the E0, etc., and indeed at FFC, I had like function pointers. So I was like, okay, found the right load address. Extra bonus stuff is like looking in the firmware, there's a bunch more references to this E0 range, and that's permanent storage. That's why you'd find like calibration information and whatnot about the device. So I did run in some snag to import it in IDA. Some instructions were not actually properly recognized because that was a fresh implementation and it was not perfect yet. Eventually it got fixed like in the following dates, but when I was doing my stuff, I was like, oh, I need to move on. And so the trick is just, you convert like the mysterious instruction into binary, and then you match it into the software manual. And by matching the 1 and 0s, you see, okay, that instruction is a multiply. And eventually, I would just, comment on these like instructions that were missing to understand better like the assembly. Okay, so now we have the stuff in IDA. We can actually start doing some work and look for like useful like code patterns. One of the first things we should consider is like what's the call convention for the functions. I think it's arbitrary for like the OS and compiler, but practically what I've seen was usually R0 or R2 R0 would contain the return value. And to call a function, you would either like pass it into R0 if it's a value or A0 if it's an address. Put like an example of memset on the slide. Also, there's a kind of like more YOLO function that just don't respect any convention. And in that case, I'm assuming it's just the compiler like optimizing for space and knowing that it can have like side effects, and that won't matter because it's under the compiler control. But yeah, be careful of the assumption you make when you try to understand the call convention and stuff. So if I can give an advice, I don't think IDA can support like type for that microcontroller. So if you want to make your life easy, you can leverage like comments, repeatable comments to just declare like the function prototype, and more substantial like function comments to just explain the function to yourself. I'm sure like, and when you revisit the thing later, like it's really handy. Another like fun one was like switch statements. That firmware like use a specific function that's going to be used to do the switch implementation. And because of that, IDA doesn't recognize the switch automatically, and I don't believe you can follow the manual switch declaration to make it work. So instead, I leverage like IDA Python to just like clean up the code by looking at all the call switches and commenting the basic blocks accordingly. So to give you an idea of the code, that's really simple. So on the left side, you have the call switch function, which just iterates over the call table and compare if it's like the right value match, and in that case, it jumps to the proper basic block, and the table is on the right. And so to do the cleanup, the trick is just extract for the call switch function, iterate a few instruction backward to recover the address of the call table, and then post-process that table. And the post-processing is also like pretty simple. You just undefine the whole table, just make sure there is no conflict if IDA misrecognizes something as code. And then you just define like words for the values and offsets for the basic block addresses. And then you comment the relevant basic block to put down the case number. So that's an example of how it looks like. It's not perfect. You don't have all the edges from the call switch, but at least you can see the case number in the basic block, which is good enough for like reversing stuff. Another uninteresting one was like log functions. The way it works is you have a generic log function that take a module name and a line number, but it turns out each module will implement their own function with a hard-coded like module name. So there's like 255 of them, and you can just automate the renaming. And the point in that is, if a function is calling, I don't know, like log heap, for instance, you know it's a heap-related function. So it gives like context clue when doing the reversing. Pretty easy IDA code. Can move on. Something else really interesting is there is locality in the code. So each function from the same module are going to be next to each other. And on top of that, like the log function I was talking about before, well, usually the first function in the module. So if you look from one log function to the next, you know that all the functions in between belong to the same stuff. So that's, once again, easy for, like, it's nice for context clues. And another like interesting thing when looking at the layout, we can see at the bottom the memory view. The left side is like this khaki color, and it's like all like the permanent data, and everything else is blue, which is code. And the interesting stuff is that there's a gap that I've highlighted in purple, and it turns out that the rightmost part is actually a bootloader code that's completely independent from the rest, and that could be interesting as well to look at, obviously. So the lesson learned so far, I would say, don't be scared of weird assembly language. If you know one assembly language, like everything else is like pretty similar. Lots of Googling help for finding documentation, like the FDA stuff. It can be really useful. Sometimes the tool you use may have like bugs and flaws. So if you're aware of the limitation and how to recover from that, it's important to be able to do that. IDA Python is really crucial to clean up stuff. It really helps. Compiler, as I said, can be like pretty funky. On the bad way, that would be like the YOLO function and the optimization that mess your understanding of the code, but might be good as well by leveraging like locality and such. And for finding the firmware address, usually it's going to be a round number, like a line address, and it can be in the data sheet, so be aware of that. Okay, now we have the stuff in IDA, we understand how it goes, so let's focus more on embedded stuff. We want to look at peripherals, because that's how the firmware can communicate with the rest of the world, and that's what we care about. So those would be like UART, for serial communication, the CAN bus, IOs, AD, analog to digital and digital to analog converters. Those are nice for finding like physical processes. And to find them, there's like two ways, at least I can think of. One is looking for interrupt handlers, and the other is special function registers. So interrupt vector table, in that case, there are two. One at a fixed address that will have like reset, log, and so on. And one that is, they can be relocated, and the address is stored in the register. And that one is nice because it has an entry point of like all the cool functions, such as like UART, timer, CAN, etc. So that's really fun to find that. If you look at the datasheets, there's a ton of those, and it looks complicated, but really, like in the application, most of them are undefined, and the ones that actually implemented are the one you really care about. Just to give you an idea of what it looks like, this is the easiest one. It triggers when there is data on your 0, and it's just going to check if there's room in like a global buffer, and if so, it's going to store like that byte of data and increment a pointer.
We're going to try switching.
Okay, sorry. Is it better? Oh yeah. Okay, so special function registers is the other way of communicating with peripheral. There's also tons of them. Weirdly, they're mapped from 0 to 400. Which is weird because usually, the 0 page is not mapped, but here it's like all the special function registers. And basically, they just work like a normal memory. You can, write like a byte or a bit to it, But what's really going to happen when you do that, it might trigger an action, change an internal settings, or read write to peripheral. And as I said before, the M32C, IDA only knows like the group 80 of the M32C. The one we have is 83, so what really happened is, in the definition IDA has of the special function register, some are just missing, but we can define them manually. And why would you do that? One of the fun things is you can cross-reference those as well. For instance, PM1 is the processor mode 1, I think, and you can see it's like 4 locations that reference that. And the datasheet is also going to tell you like the meaning of each bit in that in that special register. So like if you see something clearing like 1 bit, you can look at the datasheet and understand what it does. So yeah, why would you care about special function register? Xref is really useful for finding fun code. And you're also going to find initialization code for like UART, timer. And as I showed in my example with the UART, it relies on higher abstraction level using like buffering code and so on. So you would cross-ref those buffering code to find the actual like function that the operating system defines, and you can climb up like the abstraction layer up to the point where you find something relevant to the application you're reversing. And that's explained, like if you reversed, like some weird chip and it was writing weird data with location, that's why. Okay, so now we can also hunt for interesting code blobs. For instance, like my original objective was I wanted to find like I/O, so like UART and CAN to be able to do vuln research. Also, like finding the flash code would be nice. Like maybe I don't need to find a vuln in the processing code if I can just reflash a rogue firmware. And also like a fun one would be understanding like the physical process of the device. So how we do that? So for UART and CAN, as I said, you can find the interrupt handler leading to buffering code and then message handlers. Physical process would be more like looking at PWM, analog to digital or digital to analog converters, and usually those are going to lead you to like the business logic that you could reverse. And for the flash, that was not as obvious. So looking at the memory map, like on my previous couple of slides ago, it's being mentioned the WCR register, which is basically used to tell if you do a memory operation on the bus, wait extra time because whatever you're talking to takes too long and you want to wait. Turns out if you cross-ref that, it's only like flash handling code. So that was nice. That was a fun find. But the question is like, how do you, send a command to a flash, right? So like if you want to erase or write. So it turns out if you also follow the data sheets of the flash module, it actually explains that. And the way you do that is, once again, you write, magic values to magic addresses to instruct the flash that you want to erase or write or something. So actually you're writing stuff in the command, I think it's called the command register of the flash. So with that, I was able to find like write and erase function, but it turns out the application I was reversing could not self-modify itself. So I was pretty disappointed in that. And so it can only save, calibration data and permanence data for the application. But it turns out there is a second set of write and erase function that were in the bootloader code that I highlighted before, which is I think actually called like a monitor code. And what I realized was if you reset the pump, it could land into that code, and then you would be able to reflash the device. I didn't went that far because I found like easier route to exploit the device, but that was pretty interesting and a good confirmation that looking at the code layout was useful for identifying cool stuff. Just a second example to find CAN processing code, just to show the process. From the interrupt table, you find the interrupt handler. In the interrupt handler, you can identify global data structure. Like in this case, it's a ring buffer that is being used, every time like a message is received, it's going to add data to that buffer. And then you want to cross-ref that one. This is like much more like cross-reference this time. And eventually you find like that loop that's going to, pop a message from that ring buffer and process it. And so like, that's what like you want to go next to do like vuln research and stuff. But it turns out it's getting like way more complicated with, many blocks and, like complex code. And it's quite a mess, so in the end, I did not find like any vuln in that processing code, unfortunately. But I tried. So yeah, the lesson learned following that is, interrupt handlers and SFRs are important to locate like fun code. So like, can, UART, timers. And, if you're aware that this stuff exists, like the day like you're going to reverse a weird architecture that doesn't have a datasheet available, at least you know what kind of stuff to expect. And also, yeah, don't forget to look at the datasheet of like other components, such as the flash chip, because that explain weird behavior in the code as well. So yeah, how did it work for me? IDA Python really helped. I was able to clean up the code and get like lots of context clue from that. With the interrupt and SFR, I was able to situate myself, understand the different part of the code. But yeah, as I said, I couldn't find vulns in the CAN processing code, unfortunately, and I feel like I should probably have spent more time like emulating or fuzzing to find vulns in that, maybe. But in the end, I was also able to reverse engineer like more like the business logic of the device. For instance, it was using like a custom like CRC function to protect like data being sent to it, and by being able to forge that, we were able to forge messages and eventually like tamper with critical files on the pump, which were like basically able to achieve the goal of messing with the device over the CAN bus. So yeah, as a conclusion, don't be scared to tackle unfamiliar architecture. It's not that difficult if you're already familiar with one. If you're familiar with ARM, for instance. And that reverse engineering effort was actually like critical for the bigger project, where understanding how to talk with the firmware like help crafting payloads that we could leverage to hack the device. I put the blog if you want to like have the bigger picture surrounding this research. And yeah, I guess that's it. We have some time for the question, so you can ask me now or on Twitter. Thank you.
Thank you. This is an awesome contribution. Thank you very much for sharing. I wanted to know more about, you talked a little bit about the problems you had in IDA, just working with the instruction stream, just in certain instruction sequences that didn't disassemble correctly and things. As part of that process and just getting closer and spending more time with this, were you able to characterize some of those potential special function register usage, like in the 80/83 version of the processor versus the /80 version? You wrestled a little bit with the processor module, but I was curious if you could characterize the differences between those processor revisions as you got closer to it.
So I think my understanding of it was the difference between 80 and 83 was just different peripherals. And basically, when you open the thing in IDA, you already have the special function register like already defined. And as far as I can tell, some were just missing because that was 83 and not 80, but that was it was just the memory range was already there, and it was just possible to define something there. So yeah. Okay. Any other question? Right. Thank you, everyone. Really appreciate it.